Thank you. It's a long and wordy title, and I couldn't come up with any good options. Yeah, so today I'm going to be presenting some work that I've been doing recently. So for better or worse, this is work in progress, and I've had a lot of help from some of my students at UC Davis, Abby and Kevin. So this morning we've heard a lot about stratocumulus clouds, and I'm going to continue on that theme of talking about stratocumulus clouds, but I'm going to dive back into much smaller scales this afternoon. So again, we've heard a lot about stratocumulus clouds this morning. One thing we didn't see this morning was a global map of where these clouds are occurring. And so this maybe gives some perspective about why we've been spending so much time talking about these clouds. They cover pretty large areas of the global ocean, and they are there essentially all the time. You can see in all these box regions that the cloud fraction on the annual average is exceeding 60, 70, 80%. And so as such, they reflect, of course, a large fraction of the incoming solar radiation. They're very important for Earth's energy budget. And aerosol concentrations are known to modulate the reflectivity and fractional coverage of these clouds. And of course, we've heard a lot about those processes this morning. One thing that we didn't hear so much about this morning is that these sorts of clouds also occur in the Arctic. The Arctic is essentially whited out on this map. So let's change perspective for just a second and look at the Arctic. Here we see low-level cloud coverage as a function of season, and again, it doesn't really matter too much which season you look at. Again, what you're seeing is that we have these persistently present low clouds, and again, cloud fractions exceeding 60, 70% in these seasonal averages. So I know, again, we've heard a lot about stratocumulus clouds, so let me just briefly remind you of all of these important processes that are going on in these clouds that we need to consider. Typically, we have an ocean surface underneath, and we are getting fluxes of energy and moisture from that surface into the atmospheric boundary layer. These clouds are occurring at the top of that layer. They're topped by free tropospheric air, which tends to be warmer and less moist than the cloudy air, of course. At cloud top, there are a lot of processes going on. We have entrainment of this free tropospheric air into the cloud. Again, this is warm and dry air, so it typically helps to evaporate the cloud. We have evaporative cooling occurring at cloud top in association with that entrainment. We also have long-wave radiative cooling, and all of these processes, the evaporative cooling, the long-wave radiative cooling, the entrainment, the surface fluxes, they're all driving turbulent mixing within the cloud. Before I move on, I want to say just a little bit more about this long wave cooling. It really is mostly a cloud top feature. So here I'm just showing a profile of the radiative cooling through the cloud layer. And you can see that it is really concentrated primarily at cloud top, but that it does have a little bit of structure to it. So here I'm showing a figure from Francisca, published last year, and as many folks talked about this morning, we care a lot about the response of these clouds to the aerosol concentration and how that impacts liquid water due to, of course, its feedbacks through to the albedo of these clouds. And we heard a lot about these two regimes, the open cell regime and the closed cell regime. And today I really want to focus on this closed cell regime and understand the physical processes that are leading to a decrease in general of the liquid water as we have an increase in the aerosol concentration. And there are a lot of ideas that have been discussed about these processes. They all essentially link back to entrainment. And so before I move on, I want to spend a little bit of time talking about entrainment. So again, entrainment here is this idea that we are gaining mass into the boundary layer through mixing of that free tropospheric air above. And you can go through the literature and find lots of different approximations for the entrainment rate. Here's one that I'm showing. And you can see that many of these processes that we've been discussing show up in this equation for the entrainment rate. We have a contribution from radiative cooling. We have a contribution from droplet sedimentation at cloud top, which maybe hasn't been mentioned yet, and we have some evaporation influences as well. So I'll go through these in just a little bit of detail. I want to start at the bottom. So what can happen when you take pure cloudy air and pure clear air, so you start mixing that warm air from above, and you get evaporation of the cloud water and you get cooling, and that can actually increase the density of that mixture and lead to air that is denser than either the air that either air source that you started with. And so dense air, of course, we know sinks, and this has been referred to as cloud top entrainment instability. And the strength of this entrainment instability is quantified by this term that is appearing in the denominator here. It's not necessary to have the entrainment instability at cloud top in order to have entrainment, but it helps. Looking now at the terms on the top, again, we have a radiation term and a sedimentation term. This radiation term has actually two different dependencies on radiation in this approximation. One is that it depends on the total integrated radiative cooling through the entire depth of the cloud. That's captured by this term out here. But it also depends specifically on how concentrated that cooling is right at cloud top. Is it all occurring primarily right at cloud top, or is it more distributed through the cloud? And if it's occurring right at cloud top, then we would expect the impact from radiation to be even stronger. And that's coming through this extinction length appearing here. The sedimentation term refers here to this idea that simply by having the presence of this water in your air, it's exerting a drag on the air, and this is also contributing to a downward motion of the air. And so if you have quickly falling droplets, that drag is stronger. Wait a minute, now I think I've gotten myself confused. Anyway, it works out that what you want in order to enhance sedimentation is to have slower sedimentation so that you keep that water in this interface zone longer, and so you have more opportunity for that drag to impact the air. And then lastly, again, there's this evaporation kind of enhancement term in the denominator. This actually, at least according to the authors of this theory, mostly is an enhancement due to sedimentation and radiation again. But what it does not account for is the timescale of evaporation, which we'll talk about in a second. There's, of course, many other factors that influence entrainment rate, such as the surface fluxes and wind shear and other processes that we talked about this morning. Those aren't here, but I think that this at least gives the major processes that I'm going to talk about today. So again, I'm going to be talking about the impact of aerosol concentrations on these clouds. So I just want to really briefly also talk about the role of aerosol concentration and droplet size and how that feeds into a lot of these process rates occurring in the cloud. So if we have more aerosol particles upon which we can form cloud droplets, this means that for a given amount of liquid water, we're going to have smaller cloud droplets. So what happens when we have smaller cloud droplets? A lot of things. They fall slower. That one's probably the easiest to understand. We also get faster evaporation and condensation. That's just easy to understand by just going back to the bulk condensation equation. And we also have increased radiative extinction, meaning that with smaller droplets and the same amount of liquid water, we are reflecting more sunlight, but we're also more absorptive and emissive of long-wave thermal radiation. And this can be understood pretty simply by thinking about the extinction coefficient, and that extinction is generally proportional to surface area and the number of particles that you have. Okay, so with all of that preamble, I'm going to get back to this figure now and start talking about why we think we see this decrease in liquid water as we increase the aerosol concentration. And there are three ideas that I want to present here. The first is this sedimentation entrainment feedback, where, again, hopefully this makes sense now, if you have smaller droplets residing closer to the entrainment interface, then you have more potential for evaporation, and you can increase the entrainment into your cloud. And more entrainment, of course, means more evaporation and less liquid. The second one I want to talk about is the evaporation entrainment feedback, where these smaller droplets are evaporating more efficiently, more quickly at cloud top, and that this also can feed back to the entrainment and increase the entrainment rates into the cloud and further reduce liquid. And then the third one, which is an idea that I published last year with my student Abby, is this radiation entrainment feedback, where again we have smaller droplets increasing. In particular, this local radiative cooling right at cloud top, we're squishing all of that cooling closer and closer to the actual cloud top, and that in turn can drive more entrainment and more evaporation. And what's interesting about this is that although the total radiative cooling over the cloud may not be especially sensitive to droplet size, the strength of this really local radiative cooling at cloud top is always going to be sensitive to droplet size. Okay, so now to some of my results that I want to show today. I really just want to look into the applicability of these various explanations for why we are seeing the liquid water path decrease, and how these explanations are dependent on various environmental conditions and regions. So I'm going to be presenting two cases today. So back to a single case study. No, it's a double case study. The first, I'll start over here. I have a subtropical based case from this DICOMS 2 research flight 1, which actually got mentioned this morning as being the one that we use all the time and that we need to move away from. Here's just profiles of the potential temperature and the water vapor. Here you can clearly see where the boundary layer top is. But I'm going to move far away now from the subtropics, and my second case comes from the Arctic, based on this field campaign called ISDAC. And here are the similar profiles from the Arctic case. And there are a lot of differences between these two cases. Most obviously, of course, is the Arctic is a lot colder. There's a lot less water vapor up there. Because it's colder, you're typically going to have clouds with less liquid in them for that reason alone. But there are a number of other differences between these two cases. This Arctic case lacks the entrainment instability at cloud top. I'm running this case without surface fluxes, which is a pretty good approximation if you assume that the underlying surface is ice rather than a warm ocean. And this cloud is also mixed phase, so it contains both liquid and ice. But at these temperatures, the liquid is actually still dominant, and I'm not actually going to talk about the ice. But I just wanted to mention that even though these are below freezing, we are still thinking about liquid clouds primarily. Okay, so what did I do with these two cases? Again, I'm running simulations. I have fairly fine grid spacing. It's a much smaller domain than I think many of the simulations that we saw this morning, and they're not being run for a particularly long time because I am trying to run a lot of them. And I'm running mechanism denial tests. So I have the model running as normal with its normal treatment of radiation that depends on droplet size, and its normal treatment of evaporation and condensation that depends on droplet size. And droplet sedimentation is just an on-off factor. And then one at a time, I only allow one of these three mechanisms, these feedback mechanisms that I just discussed, to actually operate. So when I'm talking about sedimentation results today, I'm talking about these simulations where I've gone into the model code and made the radiation treatment independent of size. I've made the condensation and evaporation independent of the droplet size. And the only thing that droplet size is really doing then is impacting the sedimentation rates. And then similarly for evaporation and radiation. And then finally, I have another set of simulations where all of these processes are turned off. And for each of these, I'm running with two aerosol conditions, a clean condition with 100 particles per cubic centimeter and a more polluted condition with 1,600 particles per cubic centimeter. So the first thing I want to show is just a proof of concept. Here's the Arctic case, the subtropic case. Here's the liquid water path decrease that I get in my full physics simulations. It's decreasing like we expect as we increase the aerosol concentration. And in the simulations where I turn all of these processes off, I've fairly successfully managed to reduce this liquid water path change to 0. It's clearly working much better actually in the subtropical case than in the Arctic, but I think in both cases it's actually doing a pretty good job. And so I feel confident that I've at least identified all of the major processes that are contributing to the liquid water change. Okay, so now the question is which processes are driving the change? And so that's what I want to show you next. And I get two very different pictures in my two cases. So in the Arctic case, the liquid water path decrease seems to be entirely driven by the radiation entrainment feedback, whereas in the subtropics, it's more of actually a contribution from all three processes, with the sedimentation entrainment feedback being most important and the radiation entrainment feedback being the least important of the three. And so I'm going to try to explain why today. I don't think that I am fully there on an explanation, so if you have thoughts or ideas as I go along, I'd be interested to talk to you later. So I'm going to start by looking at the subtropical case in a little bit more detail, and showing now some of the results from my mechanism denial simulations. And what I'm showing here on the x-axis is the ratio of the entrainment rate in the polluted versus the clean simulation, and the same ratio but for liquid water path on the y-axis. And for the most part, it could be better, but for the most part, there's a reasonable correlation between the two, whereas we would expect if the entrainment rate is increased, that the liquid water decreases. So I've drawn this line kind of arbitrarily from the full physics simulation up through the origin at 1, 1, and the points, at least these two, fall fairly close to that line, and my evaporation test maybe falls a little bit outside of that. If I plot those same points for the Arctic case, I get a very different looking picture where, perhaps not surprisingly given the results I've already shown, the evaporation and sedimentation tests have no change in liquid water, and only the full physics simulation and the radiation simulations have changes in liquid water. But what's perhaps a little bit surprising is that the sedimentation only case, despite not having a change in liquid water, does seem to still have a change in the entrainment rate. And in terms of the radiation case, we're getting similar changes in liquid water, but still very different changes in the entrainment. So again, I think that there are a lot of differences between these two cases, but I think two potentially important differences between the two is that the Arctic case, again, doesn't have this cloud top entrainment instability, and the Arctic case doesn't have surface fluxes. So what I did next was rerun just the subtropical case, but I modified it in two different ways. The first thing I did was increase the inversion strength, which has the effect of shutting off the cloud top entrainment instability. And then I also reran it with surface fluxes forcibly shut off. And so I'm showing you now the results from all four of these tests on the plot. And we have quite a bit of scatter, where we can start to see some patterns emerge. The surface fluxes, or the presence or lack thereof of the surface fluxes, doesn't seem to be changing too much. The red and blue dots or symbols always fall relatively close to one another, but increasing the inversion strength much more dramatically modifies the picture that we have. This is really just the same plot, but now I'm showing these in terms of differences rather than ratios, and I'll kind of flip between them depending on which one's more convenient for my discussion as we go. So I want to now talk about each of these processes individually and see what we can learn from them. So I'm going to highlight different sections of the plot as we go through. So first, thinking about these sedimentation tests, We have two cases where we have essentially no change in liquid water, and only a modest change in the entrainment, versus these two where we get big changes in both. And these two are the ones where we have this cloud top entrainment instability present, and the other two are where it's absent. And so this perhaps suggests, I don't really want to make a firm conclusion, but it perhaps suggests that this cloud top entrainment instability is important for allowing the sedimentation entrainment feedback to operate. So to kind of look into this a little bit more, what I'm showing you now is the change in the cloud top evaporation rates. Again, this is polluted versus clean. And we only see changes in the cloud top evaporation, again, in these two cases where we have the entrainment instability, and not in these other two. So I think that's at least in line with the results on the previous slide. I don't think it confirms or denies, but it's supportive. We can also look at the profiles of the liquid water in these cases. I apologize because there's no legend, but the clean simulation is shown in the solid lines, and the dashed line is the polluted simulation. And what I think is interesting is that we see characteristically different shifts in the liquid water profiles between these two cases, which have the entrainment instability, and these two, which don't. In these two, we have this pretty notable decrease in liquid water really throughout most of the cloud layer, whereas in these two cases, most of the changes are really confined just to cloud top and don't seem to be propagating further down. Okay, so now in terms of evaporation, things get, I think, a little bit more fuzzy. So here are all of these evaporation tests in the X's. And what we see is that all of the subtropical cases are producing a reduction in the liquid water path with a variable change in the entrainment rate. So this was in terms of the differences. If you look at that instead in terms of the ratios, what you see is that the only ones really producing a change in liquid water more than 10% are, again, these two, where the only difference is the presence of the surface fluxes. So this is a little less clear. I think what's going on is these evaporation tests aren't nearly as clearly tied to the entrainment changes at cloud top, and so there's kind of two ideas I have with this. Perhaps that we are not really getting a feedback from the evaporation to the entrainment, or maybe that feedback is just being masked by other changes to size-dependent condensation and evaporation. Because in these tests, the size-dependent evaporation and condensation is being applied throughout the whole cloud, not just cloud top. And again, if we look at changes in the actual cloud top evaporation, we're seeing large differences in how much we are modulating cloud top evaporation. But again, we're getting essentially always the same change in liquid water. And somewhat similarly to the sedimentation results, we see really distinctly different liquid water profile changes, where in these two cases, we're getting decreases in liquid water in the polluted case really throughout the cloud layer, whereas in this case, with the strong inversion at cloud top without the entrainment instability, all of our changes in liquid water are really just confined to cloud top, and perhaps a little bit if you squint a lot at cloud base. Okay. So then the last thing I want to talk about is the impacts from radiation, and all of my radiation tests are actually clustered really close together here in this phase space. So in all cases, we're getting essentially the same change in entrainment and the same change in the liquid water path. Things start to look a little bit more different, though, when I start looking at changes in cloud top evaporation. Here, this subtropical case with a strong inversion is kind of doing its own thing, having a lot of additional cloud top evaporation without necessarily large feedbacks to the liquid water path. And if we look at the same thing in terms of a ratio instead of a difference, it's actually the Arctic case that now sticks out like a sore thumb, where Again, in terms of a ratio, the Arctic case seems to be responding very strongly in terms of cloud top evaporation to this size-dependent radiation. And so I would say that I've looked at a lot of different things. I haven't shown everything that I've looked at here today, but it's really still not clear to me why the Arctic case is sensitive only to the size-dependent radiation and not the other processes. One idea that I have is that perhaps in the Arctic case, the radiation is really the only process driving mixing. We don't have surface fluxes, we don't have cloud top entrainment instability. So maybe that just primes it to be sensitive to the radiation. Another factor to consider is that the Arctic case has the lowest liquid water path, and as such, it should be the most sensitive to changes in radiation. Here I'm showing how the integrated rate of cooling through the layer changes as a function of liquid water path and droplet concentration in colors. This is the maximum cloud top cooling in a local sense. So this case should be most sensitive, but I don't think that from what I've looked at, that fully explains it either. And I just, in the interest of full disclosure, what I'll say is that when I look at the simulations that I have, my polluted clouds actually always have less total radiative cooling through the column than the clean clouds. And I'm actually a little bit skeptical of this result, and I think I need to go back to the radiation scene to check out what exactly is going on. So check back with me again later, but I thought I would put that out there anyway. So just to summarize here at the end, what my simulations seem to be suggesting so far is that the sedimentation entrainment feedback certainly seems to be working as proposed, but perhaps only when the entrainment instability is present at cloud top. The evaporation entrainment feedback seems to only be operating in the subtropical cases, and that the feedback part of it itself maybe is masked by other changes that are occurring due to size-dependent evaporation and condensation. And I'm still a little bit confused about what's going on in terms of the radiation. So again, thoughts and questions and discussion are most welcome. Thank you.
There we go. Great. Thanks for the really, really cool work. On all of these plots you showed, I noticed that the effect of full physics is much stronger than any of the one effects.
Yeah, I didn't talk about that.
And so I'm curious if you have a sense of whether all of the sort of impacts, if you were to include, say, 2 out of the 3, are constructive or destructive toward one another, what the interference might look like.
Yeah, so I've actually run those simulations as well, but I didn't show them here. I think that combining, is particularly in the subtropical cases, combining the sedimentation and evaporation into one has a big influence, because by evaporating more quickly, you can feed back onto the sedimentation modulation of the entrainment rate. And what's interesting, in kind of getting back to how they interplay, is that I can actually, I can click back really far to nearly the middle here. Oops, too far. So here, when you kind of stack them all up, it looks like you need a little bit of additional interaction in order to get to the full liquid water change. But if I run with just sedimentation and evaporation, I can actually pretty much get the entire liquid water change without requiring the radiation. So another thing that may be going on is that this may be a slower response than the other 2 processes.
So is there separation of time scale here with respect to the diurnal cycle? Okay. Yeah. So is there a separation of time scales here with respect to the diurnal cycle? Like is the evaporative and sedimentation time scales for this system much
those are much smaller than the diurnal time scale.
Okay. Okay.
Yeah.
Adele, when you showed in your final slide, your summary slide said the evaporation entrainment only seems to manifest in the subtropical case, I think.
Yeah.
And I was wondering whether that's at least in part because of the higher humidity above the inversion in the Arctic case.
I think that can be a contributing factor. I think the other thing about the Arctic case, regardless of whether the humidity above is higher or lower, is that there's simply just a much smaller change in moisture due to the temperature, right? So there's only so much change in evaporation that you can get, even if it were totally dry above cloud top. Yeah.
So I'm a little bit ashamed to even ask this question because I'm a cloud person, I should know, but can you explain the sedimentation feedback? Because I know Graham's tried to explain it to me, you've tried to explain it to me before, but it never quite clicks. Like, I just don't get it.
So I think there's two aspects to the feedback that people have argued, and I don't think I've really separated them here, but one is just physically the condensate load, that if you can leave the condensate in that mixing air longer, it's going to help drag that air downwards and mix into the clouds. So slower sedimentation favors additional negative buoyancy, I think you could say. But also, if you can leave those droplets in the mixing air longer, then they should have more potential for evaporation in that air. So I think it's two things. It's both the condensate drag and the evaporation.
It's a bit off topic of what you're talking about, but when I try to contrast the Arctic versus the subtropics, in the subtropics, it makes sense to me that you actually have turbulent mixing from below because you have direct heating from the ocean. In the Arctic, things change whether you're over the ocean or just sea ice.
Yeah.
And I guess when you showed the pictures of the Arctic, it seemed it was everywhere sea ice or no sea ice. So I guess the question is, do models take into account the surface fluxes?
Models certainly take into account the surface fluxes, but I would say that there is perhaps still a little bit of confusion in the community about why in the Arctic these clouds are as long-lived as they are, in part because of what you mentioned, that we have this lack of surface fluxes. There are a lot of differences to, the lack of surface fluxes manifests to in the boundary layer structure. Often these clouds are totally decoupled from the surface, and so you actually just have this mixing layer that's separate, totally separate from the surface in the first place. Yeah.
All right, thanks.
Yeah, works. Okay. About the microphysics scheme. So for the Arctic cloud, this is a mixed-phase cloud. So I was wondering how the non-equilibrium of that is captured in this model.
Yeah, so I mean, I'm using bulk microphysics. So it has liquid, it has ice. It knows that the ice should be growing fast. I mean, it is at equilibrium at a different supersaturation, and so you do actually see in the Arctic case evaporation of cloud water in the middle parts of the cloud that I believe is driven by the ice. Yeah.
So just maybe another idea. Maybe you could try your Arctic simulation, but with full warm microphysics. That just might
just turn the ice off.
Just because the ice might be
the ice
slowing down the effects of entrainment too. Yeah, there are a lot of differences to sort out here.
Yeah,
so.
Yeah, there's a lot of differences. I only kind of focus on two, but there's so many more.
I'm wondering if you did some sensitivity studies on the grid spacing, because entrainment is essentially a subgrid scale process. So I'm wondering if some of the contributions vary with the grid spacing.
That's a great question that I do not know the answer to because I have not run those sensitivity tests. But I think that's always a concern when running these sorts of simulations, is how faithfully are we actually representing the entrainment process. And from what I've seen, I'm not sure that we really have an answer to how to do that correctly.
Any more questions? No? Then, yeah.
Yeah, maybe a naive question because I didn't do any research on the Arctic clouds. So you mentioned in the beginning that the Arctic cloud, it's, even though it's mixed phase, but it's mainly dominated by the liquid phase. Is it like commonly seen in the Arctic region, or is just special in the field campaign that you were looking at?
No, actually, the liquid-dominated clouds are very common in the Arctic. Even obviously, they're more common in the summer than in the winter. But I think even in the winter, you can find cases where you have liquid-dominated clouds in the Arctic, and that just gets back to the idea that it's pretty hard to form ice at temperatures above about -20°C.
All right. Then we thank our speaker.
Thank you.